All right, so Bruce, let's go through this and show you how this software works. First things first, let's prep the code and run it. So this is the app. We're just going to slide it over here. It'll work on Windows as well. First things first, we're going to give it a name. So 900F4470 Mudrock new HE. All right, now let's grab the spectra that we want to analyze. I put them here. And we'll process that data. Now over here, we want to select the element lines we need. So let's do sodium, magnesium, aluminum, silicon, phosphorus, sulfur. I always add chlorine for sodium, potassium, vanadium, chromium, manganese. Rhodium L-alpha, and barium L-alpha. Let's confirm elements. And add concentrations. So then here, we're just going to weight percent data over here. Copy that right there. Potassium and calcium next. Copy it over here. Titanium. Keep this at weight percent for these guys. Go back over here, grab iron, and then last but not least, barium. Enter those values and come over to CalCurves. So let's quickly orient ourselves. The graph on the left is the sodium counts per second versus the percent data for sodium that's given to us. The graph to the right is the validation plot. So this would be how much is estimated by the XRF CalCurve produced over here. Then this is concentrations. If you look up here, the equation is really important because for a validation plot like this, we want the R squared to be as close to 1 as possible, but we also want the slope to be as close to 1 as possible. For every 1% increase, we want another 1% increase. The other plots we can use, I have diagnostics here. This is just a variety of assessments of statistical models that some advanced predictors might want to use. And then this is the standards window. This shows basically the same thing S1Cal process would have shown you. I've added a relative difference indicator to give you a sense of how much the changes. So let's start by correcting sodium. First off, I'm going to use the Lucas tooth. And we're going to normalize to Compton. Now here I'm going to define Compton kind of funny, 0.7 to 0.9. Now, one big change between this and S1Cal process is in S1Cal process, you had to decide for every element how you're going to handle them. In this software, you can do it for each element individually. So I can normalize one way for sodium and another way for potassium. Could also do total counts, which would be like user-defined R or the ROI function in S1Cal process. That's really only good for metals. And then we could just go by time and call it good. Here we're going to do Compton, and I need to add intercepts. So an intercept I would like to add is chlorine, since its escape peak is near sodium. We're also going to include the L line of rhodium there. For slope, I know that aluminum influences it, so we're going to add that. And now let's take a look where we are. Our sodium line now has an R squared of 0.852. And so far, this is looking pretty good. Now, there's a couple points here that are outliers. Now, in S1Cal process, what we would do is we could deselect the standards that deviated too much here. In fact, if I want to see here, my most likely suspects, right there. In any case, here, the process is a little easier. I can just click on a point there, and it takes it out, just like an EasyCal. That could do, take those three guys out, I can toggle them right there. I can retoggle again to take them off, and I could reset all points over here. Anyway, that's sodium, which is pretty good. Is it better if we normalize to time? Not really. We'll want to keep it with Compton. We can try adding a correction for silicon as well. All right, that works. So we'll just have aluminum and silicon. When I'm done with that element, I'm going to click Update, and we'll move on to the next one, magnesium. And there we are. First off, let's take care of our intercepts. I know that aluminum is going to influence magnesium because it's so close. I'm also going to throw in rhodium L-alpha just in case. Very good. So early on, we see we've got a point over here that's predicted to have a lot of magnesium, but doesn't. You can see the big kink it's putting in my curve over here. In this case, well, first off, we know silicon's going to influence that slope, but that guy is going to be a problem, so we're going to take it out. So now we've got a much more linear path here. It's looking much better. What other intercepts could influence it? Well, let's see if time is going to be better normalization. It might be better for normalization than what I've got currently. Let's try 2.5 to 2.8, which is the traditional rhodium normalization. Nope, not as good. 0.9. And there we are again. Come over here, are any of these guys causing problems? That one. So let's take it out. So now we've got a much smoother curve. Little improvement there. Don't want to take out too many of these heavy guys, but I suspect that guy there is causing problems. Come back over to diagnostics. We're in much better shape. So, very good. This guy still has a lot of leverage, but we're just going to leave him. Update. Move on to aluminum. First things first, let's take care of silicon, who's in the neighborhood. For slope, calcium might influence things downstream here. Let's take out that guy there. Aluminum is in the neighborhood. Let's see, who else? Calcium, there we go. The escape peak of calcium is influencing aluminum a little bit. All right, with that good, let's go ahead and update and move on to silicon. Silicon, first off, aluminum, calcium, and let's do a, we don't actually need the slope correction, do we? So I can just backspace and delete it. Let's take out that guy there, and we're good. Update, and phosphorus. Now here we know calcium is going to be a problem because of that escape peak. So let's add that. We're very close to silicon, which is going to have a high reading. And for slope, might be worth adding calcium as well. We're at 0.9, that's good. Take care of those two. So for our cal curves, it's much better, 0.99. Update, sulfur. So first off, let's take care of that rhodium L line. That's going to interfere with it. For slope, let's try calcium. Nope, not much of a change. Get rid of it. Let's try silicon a little bit. That guy there is causing us some problems. See, if we look at the cal curve, you can get a sense of the influence each of these guys has to a little bit better. All right, let's go over to diagnostics. So this guy is causing us a lot of grief. but I don't want to get rid of them. We've got so few points over there. Calcium doesn't do much there. Potassium, well, you might just have to call a defeat on sulfur. Although these little guys here, well, actually, no, let's not do that. Let's try 2.8. There we go. Normalization in this case. So we're a little close to 0.7 to 0.9. A normalization 2.5 to 2.8 will look better. So let's update that. We don't have any data for chlorine, so let's go on to potassium. First things first, rhodium alpha is in the way. We're going to want to use calcium as a slope coefficient. Now, real quick, do you see this line of values there? We don't have enough decimal points. That's a problem. So the problem there is if we look at our data that we brought in for potassium, it is rounded. So as a consequence, we don't have enough significant digits to really make a good calibration curve in the low end. Hopefully that's something we can get from Harry. In any case, that looks good for now. Update, and let's move on to calcium. So calcium, we see a wide spread. First off, let's make sure we get that intercept correction from potassium, which helps quite a bit. Do you see down here, these lines? We have the same, well, no, these guys are good. So never mind, that's not the issue here. For slope, let's add silicon. And iron might be having an influence as well. There we go. Diagnostics. So here, these 2 points down over here have high Cook's leverage. So let's get rid of them. There we go. Looks much nicer, 0.981. I'd like to see a better cal curve than that. I don't know what is causing us problems here. Oh, that was a long shot. Let's try rhodium alpha in case, nope. Is there any chance? We'll leave it for now, but I reserve the right to change that later, and I'll show you how. So that's calcium, titanium. Well, first things first, let's add in barium alpha. Don't need chlorine. For slope, it's sandwiched between two heavy hitters, calcium and iron. Come over to diagnostics. Those 2 points there have quite a bit of leverage, don't they? This guy does the most. How does that affect our cal curve? Down there, if we get rid of that guy. So this would be our safe cal curve right here. We're going to go with that. Vanadium, well, we've got, well, something's wrong with vanadium's algorithm, so we'll skip it for now. Chromium. Well, first off, we need to subtract barium alpha. The slope, iron's going to have a lot of influence, so will calcium. And then those two guys remain pretty stubborn. Very good. Update. Manganese. Now, one quick note, as you probably know, you're really going to want to use the yellow filter to really properly analyze manganese. But let's go ahead and see what we can do here. Let's first subtract iron. We'll probably want iron as a slope variable as well. Not a bad idea to include calcium. And what you see is this value there stays quite stubborn. Let's give this a second to update. Let's take that out. Let's take that out. And we're not really ending up with any good curves for manganese here. We can try a different normalization. So in this case, let's do 8 to 9. That's actually looking a bit more promising, isn't it? Let's add back in these points. Not too shabby. We delete the iron intercept. Our data looks a little nicer. These two guys are still swinging wild, but we need to add a correction to chromium. And long shot barium. Let's see how iron influences this now. Yeah, I'm not a fan. All right, so let's do it like that. We'll leave those two wildly variant, which is unfortunate, but we do have an R-squared of 0.9. Let's go ahead and go to iron. Very good. Just a point of contrast, 2.5 to 2.8. And we get much less of a cal curve. 8 to 9 worked quite well. In fact, let's just test 10. A little better even. All right, intercept. We know manganese K alpha influences it, though probably not that much. Go ahead and do a slope correction to calcium. And we're still left with that basic state of affairs. Let's try 15. A little better. We'll go ahead and leave that. So we'll click update. Now I'll click save and download the model. So now I've got my calibration curve. If I come over here, copy it over here. Now the calibration file is right here. I give it the serial number of the instrument, 900F4470. You can name this whatever you want. Mudrock new helium quant. So what do we do with that file? Well, let's say I have data. So I'm just from this sample again. Browse, and we'll grab that cal file I just created. So that one right there. And quantify. And then this is kind of like the chem test sheet where it just pops out all your data as you were hoping to have it. So we see here our top line there for HR1 is 28.4% calcium. That's a bit off. I don't like that. We might need to review some of calcium's corrections actually. 33, that's a little closer. 34. Iron was 0.26, iron 0.21, that's pretty good. 0.26 again. All right. As is always the case, you want to double check and validate, and you can make decisions here based on how things look in the other data set. Now, let's say you wanted to, all right, so we're gonna call that good. Let's say you wanted to edit a cal file you had already made. Well, easy to do. We're gonna go ahead and grab it here, use cal file, process data, and voila, our counts are back, confirm those. Our values back, enter those, and then our cal curve comes back with the same corrections we'd given it earlier. We can edit it and save a new one using this as a template. If you wanted to build new calibrations from this, so for example, let's say I have new spectrum, for example. Let's see, what can I use as an example? I don't have another instrument with these same standards, so we'll just grab the guys again. Actually, no, I just need 41 spectrum of something else, don't I? So let's do that. So we're going to grab a whole different set of data. We're going to grab, where do I go? Just a moment, because you need to get the standards to be the same amount. And that's Harry's set, and don't really, well, yeah, I don't really have another set of his. We're going to cheat a little bit and just grab a random assortment of these guys. We just need 41. So 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41. We'll see if this doesn't break it. Process that data. If I want to use those new spectrum, it's going to pull it from the new ones. There we go. Confirm those elements, enter those values. If I come over to my cal curves, they're going to look terrible because I just added noise. Point is you can go back and forth between different standard sets. So once you build a calibration, you can apply all those calibrations. So in this case, this would be like importing from a new instrument. So in a nutshell, that is the app as a whole. It's available online. In fact, we can test that out. If we come over to, where is the address here? We open up a new tab. We come here at that website. I'll need to restart the server. But anyway, it'll be available there. In fact, why don't we launch it real quick? So start, log in there. Then let's launch the Shiny server. There. If we come over here, we should hopefully be up and running in just a second. So anyway, point is, we can host this remotely at a website, and the website works exactly the same way. Anyway, that is a rough rundown of the app, and let me know if you have any questions. Thanks, and bye.